and he is from Yankee Tank Creek Observatory, CEO.
You'll do I have to push anything? So yeah, I like the pretentious name, a nice pretentious name for my backyard observatory. I think it's wonderful. So what I'm talking about today, of course, is autocorrelation techniques with small telescopes. Let's see, does this thing work?
You might have to push it up.
Hmm?
You might have to point toward that.
Oh, one of those point things. Huh?
It's that button right here, that arrow.
Yeah, okay. No, but I bet, okay. So this is Yankee Tank Creek Observatory, a sky pod in my backyard. And the challenge for those of us who live in places like eastern Kansas is being able to get close enough to actually successfully measure relatively close and therefore astrophysically interesting double stars. In seeing conditions that are good when they're at 3 out of 5 and are usually just below 3 out of 5, between 2 and 3 on this 5-point scale, we get really good seeing about 3 times a year. So what I'd like to do is to assess autocorrelation data reduction techniques using essentially an 8-inch telescope under less than ideal conditions, which always prevails in eastern Kansas. Compare it to Lucky imaging under the same conditions, and to see about the accuracy of such measures. This is purely amateur equipment, and I think that's good because most people who are interested in double stars have exactly the same sort of equipment. A 205 millimeter Dahl Kirkham, rather long focal length, an off-the-shelf Losmandy German equatorial mount, an off-the-shelf image source DMK 21 camera with a tiny chip. For increasing focal length, a standard $50 Orion Shorty Barlow, and the queen of amateur reduction packages, Reduce. The only thing that's missing here is a flip mirror if you want to stay sane when you have a when you have a really tiny field, you need a flip mirror. So methods for each night's run. First thing I do is I establish plate scale and orientation, usually using rectilinear pairs that Bill was nice enough to put in the rectilinear catalog, and also drift, star drift. Integration times with this camera between 8 milliseconds and 66 milliseconds. Magnitude limits 8, 9 magnitude pairs, so long as they're equal. I take a minimum of 4 videos per double. I start out with I started out with taking only 400 frames, and now I'm up to 1,000 frames. And for wide pairs, maybe as few as 100 to 400 frames, and integration times up to a second. These things come out as AVI files, so they have to be transferred into bitmap images, which is done with a freeware program. For autocorrelation, I use Florent Los's Reduce, his latest version. I run autocorrelation with enhanced spectrum. This thing gives you a series of correlograms that are masked between very light masking, which is an S1, to a very heavy masking, which is S9. And I use the least amount of mass that I need to get a real separation. And so what it amounts to is for each double you get 4 to 5 actual measures, and that gives you at least a minimum in terms of being able to figure out errors. For Lucky imaging, this is what I call Ed's lazy Lucky imaging. So with Reduce, and I'm not saying this is the best way to Lucky image. With Reduce, you have a thing that you can sort on max signal. Then I pick the best 10% for most of my pairs, which would amount to about 100 images. These are stacked and then they're measured, and so you get the same 4 to 5 total measures with the Lucky imaging as you would with the autocorrelation. And all of these data are saved into Reduce. Reduce has a handy logging program that you can save all the data. Here's an image. This is 36 Andromeda, a 6 magnitude pair. The separation is about 1 second at an angle of 326 degrees. This is a well-known orbital pair, and with this little 8-inch telescope, we're getting OC values that are comparable to the interferometric values from larger instruments. So I got really jazzed when I saw that. I thought that was pretty cool because there's lots of astrophysically interesting pairs that are 1 to 2 or so seconds in separation. Just technically, it's an S5 correlogram. It is the best 500 out of 1,000 images. 16 millisecond integration, nominal f50 and this was a good seeing night. This was seeing night of 3. Whether I would have gotten this on a 2 night, I don't know. Because the one thing I do know about this is this has nothing to do with being a speckle program, because this scope is not big enough to get speckles. So what we're doing is we're autocorrelating on pixels, not on speckles. Here's how that particular measure compares. As Bill will tell you, I like to look at the history of my pairs. So this is the entire history of observation of this particular pair with theta and rho converted to Cartesian coordinates, just to get an idea of how we're doing in terms of the measure. This is what one of these images looks like. This is a single frame. This is 1 out of 1,000, and you can see it's just a smear of pixels. Now, for the lucky imaging, Reduce has a nice thing. You can quadplex, and then you can do a routine that's called surface. And so in surface, what you do is you say that's A, hit it, that's B, and then it does a surface analysis, which is comparable, which compensates for the artificially close separation you'll get with such pairs when they're that close together. This is what apparently some of the professionals in France use, and this is the result of the lucky imaging. 2 fairly well separated stars, but when I measured it, I got a really deviant OC measure of almost 2.5 degrees, which means the centroiding wasn't very good. So if we start looking at this stuff in terms of what it amounts to in the last 15 years of measures, all the black circles are from WDS. These are interferometric ones. Here is my measure, which is essentially right on the ephemeris value. Here's the lucky imaging, which it looks like 2.5 degrees looks like a really gross error, but when you look at the scatter of all of the previous measures of the star, it actually is not all that bad. This is how bad it can get. This was early in my program when I was doing only f22.5. This is 44 booties. You notice that there's a little distortion in the correlogram here. However, if you look at it, you'll see that Reduce is quite successful in taking a 1.2. Oh, by the way, I apologize for those 3 values there. It really is just 1.3 seconds. I forgot to do that. I'm sorry. I forgot to round off. It actually is it's actually very good even at f22.5 in terms of at least agreeing with the ephemeris value that can be generated. This is about as bad as it gets in lucky imaging, so far as I can see, and yet Reduce still was able to come within 1.2 degrees of theta. Not terrible, but what you see with the lucky imaging at this particular point is that your error terms become really big. So this has an error of almost 1.6 degrees. So here's some more plots. This is a polynomial fitted to a epic versus x. So we've converted things to Cartesian coordinates x and y, taken only the x values and regressed them against the epic. And you can see that Reduce is very good at figuring out the separation, because separation is dominant on this particular x-axis. Everyone is straight on to the ephemeris, auto, and lucky. But when you get to the y-axis, for which angle is dominant, what you see is the lucky image is falling a little bit off. Nevertheless, still not bad compared to the scatter of other measures, of other recent measures. So one thing that amateurs face, because we don't know all the stuff you guys do, is how do you evaluate your images, and how do you evaluate your measures? And in many cases, there's neither a rectilinear model nor an orbital solution in which to do that. So I kind of ginned up my own. So let's see what you think about this. So this is a 7.5 magnitude variable, STF 425. Here's a single best. This is my single best of 1,000 of this particular pair at a 33 millisecond integration. And this is the correlogram. Whoops. This is the correlogram that emerges from that, from correlating the pixels. And so I obtain something that looks fairly reasonable, given the WDS history, about 60 degrees and about 1.9 second separation. But I have no way of evaluating that. So how do I evaluate it? Well, here's what I'm kind of proposing. You take advantage of that, of those regressions of epoch on X and epoch on Y. So what I did was I took the entire history of observation, no weighting, which is probably not so good. I'd hate to be that guy. And I simply do a linear least squares, and for the x-axis, what that gives me, and I include my measure, so that gives me an expected value of X, and of course I have my observed value of X. Then I do the same thing for Y, so that I have expected value of Y and observed value of Y. Then I convert it back to theta and rho. I convert the expected back to theta and rho, and then that gives me an expected at time of observation, for which I can do my OC, and I see that I'm about half a degree off, or a little bit more in theta, and not very off in rho at all. So I'm now using that as a way for an internal check in terms of being able to get OC values when we don't have either a rectilinear or an orbital solution. So how are we doing with lucky imaging? Well, with these techniques, with this telescope in my backyard, what I'm seeing is, so this is the major deviations are in angle, not in separation. Everyone's doing well in separation. So this is the OC of theta, and this is rho, so it's OC of theta is a function of rho. And what we see is that as we get closer, the spread off the OC value gets larger for these pairs. And we see considerable spread even in this area where lucky imaging does a pretty darn good job in the 2 second region. But when we go to autocorrelation, what we see is that there's a much tighter grouping of these things around the expected OC value. And so at least for the way I was doing lucky imaging, for my backyard, for my seeing conditions, I think that autocorrelation on pixels works pretty well for the average amateur to get close enough to do something that is actually interesting. You can do lucky imaging and perhaps a better form of lucky imaging, and you can do quite well up to about 1.5 second separation, although you will suffer because there's greater scattering of the measures than there are with the autocorrelation. And that autocorrelation seems clearly superior when to lucky imaging under adverse conditions, when doubles are less than 1.5 inches, 1.5 seconds of separation. I haven't gotten it. I don't think I've gotten as close as I can. We'll see how that goes with the new spring campaign. It's too cold in Kansas for me to get out in the backyard until March. So I'd like to thank Florent Los especially for much of his advice on reduce, Brian and Bill for honoring my many requests for data. I don't know if I'm a big data requester, but I feel like I overburden you guys with as much as you do. Bob Royce, who built the telescope, he's truly an exceptional optician. Russ for hours of talking about reduce on the telephone. And to all the organizers who made this such a delightful meeting, and I thank you very much.